Okay, let's dive right into this explainer. When we look up and spot a drone, we usually just see the physical hardware, right? The spinning motors, the battery, maybe a camera lens. But the real magic, the absolute lifeline that keeps that aircraft safely in the sky, completing complex missions instead of crashing into a tree, is a completely invisible stream of data. Today, we're unpacking the incredibly sophisticated communication architectures that make autonomous flight possible. Because a modern drone, it's not just a flying camera anymore. It's a highly secure flying network node.
Now, this is where things get really interesting. When a drone faces intense electronic jamming, how does it actually survive? This question exposes the high-stakes reality of crowded airwaves and active electronic warfare. I mean, drones today aren't just dealing with a little bit of static on the line. They are regularly flying through areas saturated with intentional signal disruption, from heavy military radar interference right down to the dense, chaotic radio noise of a modern city. Keeping that digital heartbeat alive in those conditions is literally a masterclass in modern engineering.
So here is our roadmap for today. First, we'll cover the challenges of drone communication. Second, RF specs and anti-jamming. Third, key data link protocols. And finally, we'll wrap up with remote ID and airspace.
Let's start with Section 1, the challenges of drone communication. Before a single byte of data even leaves the drone, it faces an incredibly hostile environment. We are talking about extreme electromagnetic threats, high-power microwaves, broadband noise jamming, or even high-altitude electromagnetic pulses. If a drone isn't physically and digitally hardened against this, that interference can just bleed right into the system through the antenna or tiny gaps in the chassis. The result? A complete communication blackout, or worse, a hostile takeover of the drone itself. The military has strictly defined survival standards for this stuff, like MIL-STAN 461, and we're seeing those exact same standards become absolutely crucial for commercial drones today. Moving on to Section 2, RF specs and anti-jamming. Let's look at how the physical radio waves are actually protected. The easiest way to understand this is to think of radio frequency bands like highways. The 1.4 gigahertz S-band, that's your dedicated long-distance express lane. It's used strictly for critical telemetry, giving the drone up to 40 kilometers of range without getting bogged down by civilian Wi-Fi interference. On the other hand, the 2.4 and 5.8 gigahertz bands are like massive multi-lane local highways. They handle the heavy traffic, like streaming 1080p high-definition video. They use something called OFDM technology, which basically just prevents the video signal from getting confused when it bounces off city buildings. By separating the critical flight controls from the heavy video feeds, the pilot never loses control of the drone, even if the video feed totally lags out or drops. But what happens if an adversary actively tries to block your express lane? Well, that's where frequency hopping spread spectrum, or FHSS, comes into play. It is the ultimate survival tool. Instead of driving in a straight line, FHSS constantly switches lanes to dodge roadblocks. Here is how it actually works in the real world. The drone's signal doesn't just sit on one predictable frequency. It hops around the spectrum using a highly secure pseudo-random code that only the drone and the controller know. And it does this incredibly fast. We're talking synchronously jumping over 2,000 times per second. Because it's hopping that fast, the drone's signal just becomes a massive, unpredictable blur to anyone trying to block it. A hostile jammer can't lock on because to them, the signal just looks like random background noise. But listen, no matter how good the automated frequency hopping system is, sometimes things go wrong, and a human pilot needs to instantly grab the digital stick. For that immediate, close-range human intervention, drones use mature, ultra-low latency link buses like FrSky. This bypasses the complex networking to guarantee that if you need to perform an emergency manual takeover, your reflexes translate to the motors instantaneously. All right, Section 3, key data link protocols. We've got the radio connection locked in, but what language are these components actually speaking to each other? It turns out a modern drone is multilingual. There are 3 distinct data protocols at work here: Mavlink V2, SIFL, and XRCE-DDS. They dictate how the drone speaks to the ground, how it talks to its own internal sensors, and how it communicates with its onboard AI. The best way to understand this is to compare Mavlink V2 and SIFL. Mavlink handles the external stuff. It's the air-to-ground telemetry communicating with the pilot. SIFL, on the other hand, is the internal nervous system. It's decentralized and connects the battery, the electronic speed controllers, and the motors. You absolutely don't want a hacker taking over your external ground link, right? But you also don't want an internal wiring glitch shutting down a motor mid-flight. 2 very different problems requiring 2 completely different protocols. To lock down that external air-to-ground link, Mavlink V2 stamps every single piece of data with a SHA-256 digital wax seal. It authenticates the message, proving to the drone that the command actually came from the real pilot. It completely prevents an attacker from recording a legitimate command and replaying it later to hijack the drone. But, and this is a really important caveat, just putting a wax seal on an envelope doesn't make the letter inside invisible. To actually encrypt the data payload so no one can eavesdrop on your telemetry, you still need a VPN or AES-256 hardware encryption on top of Mavlink.
Meanwhile, inside the drone, SIFL uses a brilliant stateless publish-subscribe architecture over the CAN bus, which, I know, sounds like tech jargon, but here's what it means in plain English. There is no master computer bossing everyone around. If a massive burst of interference temporarily fries a sensor, that single node can reboot and rejoin the network in less than 10 milliseconds without freezing up the rest of the drone. It's decentralized, meaning a single point of failure won't bring the whole aircraft tumbling out of the sky.
And what about the brain? For high-speed artificial intelligence, the XRC DDS protocol acts as a direct bridge. It connects the drone's flight controller straight to an onboard companion computer, like an NVIDIA Jetson, with incredibly low latency. We're talking under 10 milliseconds. This is the superhighway that lets the drone process camera feeds, run heavy-edge AI algorithms, and autonomously dodge a tree branch in real time without needing a human pilot to tell it what to do.
Finally, Section 4. Remote ID and airspace. Even with all this incredible tech, these drones still have to share the sky safely with helicopters, commercial jets, and strict regulators. Which brings us to a very specific number, 250 grams. Under the FAA's Part 89 mandate, if a drone weighs more than 250 grams, which is roughly the weight of 2 sticks of butter, it has to be a responsible digital citizen. It is required by law to carry remote ID. Think of remote ID as a digital, continuously broadcasting license plate that publicly shares the drone's unique ID, its 3D location, and its speed. Now, there are 2 ways this license plate is shared. You have broadcast remote ID, which uses standard Bluetooth 5.0 or Wi-Fi to shout its location locally. It's perfect for a park ranger or local law enforcement checking up on a nearby pilot. But if a drone is doing long-range delivery, way beyond the pilot's visual line of sight, we use network remote ID. That uses built-in 4G or 5G modules to stream the drone's telemetry directly into global cloud platforms via cell towers. And that network remote ID, that's the secret sauce for the future. It enables cloud-based unmanned aircraft system traffic management, or UTM. Because these drones are streaming their location and flight paths to a central cloud, the system can perform strategic deconflection. It mathematically verifies flight paths to prevent mid-air collisions before the drone even leaves the ground. It's basically air traffic control, but it's entirely automated, run by algorithms, and scaled to handle hundreds of thousands of drones sharing the same airspace.
So, knowing all of this, knowing that we have these multi-layered, ultra-resilient communication architectures, from frequency-hopping radios to decentralized internal networks and global 5G tracking grids, it leaves us with one pretty provocative question. The data links are clearly ready, but are our cities actually ready for skies filled with dense, autonomous drone swarms? It's definitely something to think about next time you hear that buzzing overhead. Thanks for joining me on this explainer. I really hope it gave you a totally new perspective on the invisible networks flying right above us. See you next time.